Good job. Rightio. Okay, this is actually take 2. I didn't switch to Photoshop before I did the last one, so I just recorded myself speaking for 40 minutes. I have remembered to record the Photoshop tab this time, so yeah. Anyway, this is just a video where I'll go over chapter 4, 5, and 6 stuff, see if I can learn from it. Maybe I can help a few people, maybe no one will watch it. Either way, it's just good for revision. Alright, now first off the bat, let's just go over Redox basics. Now, this is the sort of thing that if you don't know it by now, you're sort of not going to do well on the SAC. To be a bit mean, but like if you don't know that reduction means the gain of electrons, that oxidation means the loss of electrons, it's not looking good for you. It's also reductant, knowing that a reductant or a reducing agent, the same things. They both lose electrons, not to get them confused with gaining electrons, and an oxidant or an oxidizing agent will gain electrons, as the oxidant oxidizes it takes them, so it himself gains. Now, an important distinction to make: a lot of people see stuff like chloride ions, and they think that's an oxidant. It's a common misconception because everyone knows chlorine, very powerful oxidant. It's very eager to take electrons, gain those full outer shells, and become Cl-. This really wants to become Cl-. Once it becomes Cl-, it's happy. It doesn't want to do anything else. And short of reacting it with something like fluorine, it's just going to stay like that. It cannot oxidize something further. Mix it with lithium, it will not oxidize lithium. Alright. Oops, sorry. One moment. I need to erase this icky stuff. Okay. Now, oxidation numbers, another thing should just be water off the duck's back for us now. Oxygen, -2, unless it's peroxide or oxygen fluoride. You never see this in the real world, it's just the sort of question they have to see who's paying attention. Hydrogen, +1, unless it's a hydride. Again, not very common, but it's just the sort of thing they like to put in there to trip people up if they're on autopilot. A couple of examples: find the oxidation number of oxygen. This is a perchloride. It's bleach. It's probably one of the only times we ever see perchloride in the real world. We know that this is +1. There's 2 of them, so they overall contribute +2. You can see that this is a neutral ion, a neutral compound, sorry. So to make it neutral, each oxidant has to contribute -1 or -2. So that means the oxidation number of oxygen in hydrogen peroxide is -1. Then we have this one. And this one, it's a bit more difficult. It's the sort of thing that might trip some people up, because they do it in the different order. They do nonmetals, then metals. That's not right. You'll see why here. So oxygen, -8, obviously. Now, potassium, it gives up 1, and you might think it's a metal. It can donate a lot more. Metals generally don't like their outer shell electrons. But once potassium gives up its electron, makes the oxidation number +7, sorry. -7, sorry. The potassium has a full outer shell. It's very stable. Chlorine, on the other hand, it doesn't like to give up its electrons. But in this case, the ionization energy for potassium, once it's donated 1, is actually higher than chlorine even. So all 7 of chlorine's outer shell electrons are taken to make this compound neutral. So it becomes plus 7 Cl. If you know about chlorine, it's generally a very powerful oxidizing agent. So overall, this compound is a powerful oxidizing agent. It's used in quite a bit of organic chemistry. We'll learn about that later. Now, probably one of the more important things to know, in fact, I would argue the most important thing to know, is a simple Daniell cell. This is what the sec's going to be about. It's what we're going to do in class. It's the questions we're going to have to answer. We will, without a shadow of a doubt, have to draw a Daniell cell and label it completely. Now, I've actually put in a little thing here. This Daniell cell is wrong. Not because it's undetailed. Well, yes, because it's undetailed. But something about it is drawn wrong, and you won't get marks for it. I'll mention it at the end of the video if I remember, or if I forget. Someone leave a comment, and I'll get to it. Now, one of the best things to do immediately is to find out what's being oxidized, what's being reduced. We have our Bible, or the electrochemical series, with us in this sec. You should probably know by now, silver metal is, well, it's not a powerful oxidant. The silver metal ions are very powerful oxidants, whereas iron metal is a fairly powerful reductant. But if we're dealing with other things, let's just pretend we've never done a question about redox. We just know these. We don't know if silver's a powerful oxidizing agent, if iron's a powerful reducing agent. We just have these two. We go the highest one minus the lowest one. The highest one is reduced, so this reaction occurs. The lower one is oxidized, so this reaction occurs. To find the overall potential difference, we do 0.8 minus 0.44. Gives us 1.24, unless I'm bad at addition, which is very much possible. So yeah, we're given this, and just by using the which one is greater, the one that is greater is oxidized, is reduced, sorry. As it is in the electrochemical series, like, notice these are all reduction reactions. And the one with the lower one, you have to flip it, so it becomes the complementary oxidation reaction. Now, I'll just go over this. This also should be the sort of thing that, we get by now. It should just be water off the duck's back, scribble on, and we know exactly what we're doing. But just in case, I'll go over it. So, be able to identify the electrodes. We learned from the last one, iron metal is being oxidized. By definition, the anode is the site of oxidation. And by definition, you don't spell anode like that. By definition, the cathode is the site of reduction. In a primary cell, and also in a fuel cell, and also in a secondary cell, while it's discharging, cathode positive, anode negative. Another thing to note is which way electrons flow. Miss says the A to C thing. That's fine if you want to use that. You can also just remember anode oxidation, losing electrons, they have to go somewhere, probably to the place where it's accepting electrons. So just like that. E minus, make sure to label what it is. That arrow could mean anything were it not for the label. We also need to know where the ions go. This is a potassium hydroxide salt bridge. It has K plus and OH minus. Don't be tripped up. The plus does not mean this cell is becoming more positive. I don't know what the plus is there for. I've never known what it's there for. It's very annoying to me personally, but we just have to sort of deal with it. It is accepting electrons though, this half of the cell. So it stands to reason it becomes more and more negative. To balance the charge, we have to have potassium move to this one, because potassium is positively charged. This one, on the other hand, is losing electrons, and more Fe2 plus is becoming present in the cell. To balance this, we need more hydroxide. Let me just have 1 second. Ooh, okay. This is actually a very bad designed thing, because the hydroxides will react with the iron to form FeOH2, the solid. Sorry about that. Yeah, usually we use nitrates for the salt bridge, because nitrates don't form any soluble compounds. Well, they do, but not in our course. So if it's asked to identify a chemical for the salt bridge, always say nitrate. Now, what's some other stuff we need to do? We're not quite finished yet, are we? Overall reaction. Yes, we haven't done the overall reaction. Again, this is an easy one. 2AgAQ plus FeS goes into Ag2S plus Fe2 plus AQ. Yeah, easy one. We don't have to worry about any cohas, any oxygen, any water. It's just nice and straightforward. Oxygen reductants. It is stressed heavily. You need to know exactly what the salt bridge is for. Whoops, I did not mean to erase it. The salt bridge not only completes the circuit, but it allows for ions to migrate and to balance the polarity. Were it not for the salt bridge, this would just become extremely negative and this one would become extremely positive. And because it's so negative, the electrons wouldn't want to go to it. It would want to stay with its positive one. So it's balanced, opposites attract and all that stuff. Yeah, sorry. I forgot it in my first take and in this one. I was supposed to say this part first, but a galvanic cell is a cell that generates a current using redox reactions. A galvanic cell is a greater definition for both fuel cells, Daniell cells, zinc, nickel. There's so many I can't name, nearly approaching half of them, but it's just that, a cell that generates a current using redox reactions. Alright, that's enough of the basics. Let's move on to more complex cells. Whoops. There. Alright, so sometimes we can get a nice and disgusting diagram like this, where it's not a Daniell cell. You can't just tell by looking exactly what's going on. So you have to sort of look at it for a moment, look at the labels and break down what's really happening. Now, were this cell connected? And we know this is the anode, so electrons have to flow up through here into here. This stuff here is being oxidized, and the electrons are going from here to the anode, going all the way up around here to the cathode. There's usually something in the middle, otherwise it just produce heat and be very useless. The cathode material will be reduced, and along the way something is powered. With this one, you just have to look at it for a while. You'll get it eventually. Sort of try and, transform it into your minds to two half cells if you want. I don't know, it works different for each person. I mean, that's assuming we even get something like this. We might not. Alright. We also have to worry about it here, the insulator. The insulator does not allow the anode chemicals and the cathode material, I should say cathode chemicals as well, that it does not allow the blue to mix directly with the green. Were it able to, it would just produce heat, and that's completely useless unless you want a slightly more dangerous hand warmer, as usually batteries have some dangerous chemicals in them. Its real purpose is to, of course, keep them separate, but it allows ions to transfer through them. It's almost like a different version of a Sol bridge. It allows the completed circuit and for ions to pass through. It's very important for this and for all galvanic cells. Now, when this cell, when it discharges, and it's connected to something or other, we get reactions. Reactions in the real world are nowhere near as simple as those in a nice little Danielle cell. They often look like this. They do have correct subscripts. I'm sorry about that. I couldn't find how to do that on Photoshop. I don't think you can with some fonts, but whatever. You understand. With this, I left this one a bit blank so we could practice Cohas. Now, if you'd like, you can go pause the video and do this one on your own. It's definitely something you need to know before the SAC. Alright, so this one, it's not too bad, it's not too messy. You'll notice this one has 2 hydrogen. We don't have to balance with oxygen, because oxygen we have 2 here and 2 here, so it's already balanced. This one has 2 more hydrogen, so you have to add 2 hydrogen to this side. But if you stop there, it's not actually right. Because you can see up here, we have hydroxide ions. In the presence of hydroxide ions, a solution becomes basic, which means that there aren't that many hydrogen ions, so this reaction wouldn't actually occur. To account for this, we must add enough hydroxides on this side to make every single hydrogen become a water, and we have to add the same amount to this side to keep it balanced. Like matter cannot be created or destroyed, that sort of thing. Sorry. So yeah, once we do that, we get 2 water plus 2 NiO2 plus 2E minus goes into nickel hydroxide. Oh, whoops, that's not supposed to be on here. Just be outside. Don't get that mixed up on the test. And then 2 hydroxide ions. Definitely know how to do that. Now, we also need to know how to derive a discharge reaction from 2 half cell reactions, or no, 2 half reactions, sorry. This one, it's a bit it confused me a lot the first time I read it, as Evo is positive in this one, but you have to remember that this is the oxidation reaction. So if I were to write sorry, I should have had this ready ahead of time. 2OH minus AQ plus cadmium solid. The E of O would actually be negative 0.81 volts. But the site that I stole this from already did the courtesy of transforming it into its oxidation reaction. And as a result, the sign of this flipped. Now, to find the discharge reaction, it's as simple as just adding these. Just add them. I'm not even going to write it, for one, because I'm using a mouse, and I don't like using a mouse to write things. And for two, it's just very, very simple. For this one specifically, we just add the E of O's. But if we were to use this value, which we should, because we are very rarely given this thing in oxidation form, you have to use the reducing form. This one's obviously a lot lower than this one, so this one will be reduced and this one will be oxidized. So you have 4.9 minus 0.18 is 1.3 volts. Alright, so yeah, relatively easy question, even though that was supposed to be for the complex cells. Alright, it's a bit annoying, this one, since strictly speaking, electrolytic cells aren't until next area of study, but we're learning them now for some reason. Well, I'm not going to argue. Alright, in a secondary cell, products stay in contact with the electrodes, which allows recharging. Now, this distinction might seem a bit insignificant until you actually think about it. You think if the products stay in contact with the electrodes, electrons can still flow, but they don't want to, because, they've already flown to the one that's a more powerful oxidant. But if we get something like a dreadful looking car battery, sorry, that looks like absolutely horrid, and I also made it wrong because there's the line in the middle. Yeah, if we get an absolutely disgusting looking car battery, and this cell that I've scribbled all over in my first version of this, it actually forces the electrons to go the other way. It forces them into the anode, or what used to be the anode. And in doing this, the electrons are actually sort of dragged out of the cathode. Or what used to be the cathode, sorry, to not get those mixed up. Now, seeing as the definition of the anode being the site of oxidation, this part, which used to be the cathode, is now having its electrons dragged away. This becomes the anode. But do not forget, as a secondary cell recharges, the anode is positive. Very important. I'm quite sure there will be a question on that. And the cathode is negative on this side. Now, there's something important to note about the secondary cell. Is a problem you don't really notice with primary cells. Primary cells, use them once, they're done, toss them. Or I think you're supposed to give them to battery recycling people. I'm not sure, I've never done that, I just toss them. I probably shouldn't, I should look into that. But either way, a unique problem arises with secondary cells. Because we use them over and over and over, there are little side reactions that occur. It might just be a small, insignificant reaction that happens like with the reductant and the cathode, or the anode, sorry. And as it occurs and it occurs over time, as you recharge it, as you discharge it, it eventually degrades the battery's, capacity. So it can no longer get to a 100% charge. And it gets black stuff on it. It doesn't get black stuff. It might get black stuff on it. I'm not sure. That's just how I'm drawing it. So as you use it and you use it more, side reactions happen. Something might crystallize here, so it can't stay in contact. Something might leak out. A slew of things can happen that just eventually make this useless. It happens slowly, but it does happen, and it is a very real problem with secondary cells. I would go as far to say, if our chemistry in the public domain is about secondary cells, there would be a question talking about side reactions and the degradation of secondary cells. But I'd assume it's going to be on fuel cells anyway. Now, another thing to know, when we have this being the forward reaction of a battery, of this cell, the forward reaction, so the opposite of what's drawn here, to find the recharge reaction, it's very simple. We just move everything to the other side. Just flip it. Done. An important thing to note actually is the thing that is recharging it, it has to have a higher potential difference than negative 0.13 in this equation. So, I mean, it has to have a higher potential difference than positive 0.13 because the cell is negative 0.13. So, it's weird. You can charge a secondary cell with another battery, even though the battery is a galvanic cell. Yeah, but the more important thing to note here is you want a discharge reaction, reverse the forwards reaction. You want a discharge reaction, yeah, I just said it. You want a recharge reaction, flip the discharge reaction. Done. Easy. Alright, now on to what is probably the most important thing of this unit. Fuel cells. A fuel cell is a specific kind of galvanic cell where the reactants are provided constantly. Here's just a simple version of it. Hydrogen gas goes in there, oxygen gas goes in there. Hydrogen gas is combusted. We don't like to think of it as combusted, but it's the same definition. They react, they produce some water, some carbon dioxide, and it's all good. It's important to know a fuel cell will produce the same amount of energy as combusting something, assuming complete combustion of both the fuel cell and the normal combustion. It's the fact that in a fuel cell, the energy is so much more easily obtained. It goes right through there. Just chemical to electric, one step. A lot of heat actually is produced, but it's still so much more efficient than, say, having to, pump it into the car's engine. It lights, it makes the pistons, and, a car engine is so hot. There's so much wasted energy that you need a cooler, for the engine. This thing is so much more feasible, and some fuel cells actually go as far to use the excess heat as energy. And I remember those being 85 to 90% efficient, which is it's really good. You might get a question saying, well, if burning the hydrogen gives just the same amount of energy, why do we use a fuel cell? Fuel cells are more expensive. Though that may be true, if you just purchase it, over time, since it's so much more easy to collect the fuel cell's energy, you need to burn less hydrogen. So overall, you use less fuel in a fuel cell than if you were to combust it. Now, that means it's more cost efficient, and it is much more carbon, well, not neutral, but less carbon, because you have to burn less of it. Now, considering that this hydrogen fuel cell is one of the more common ones. There's an entire point on the study design that talks about storage, production, transportation of hydrogen. Those are some fairly easy to understand. So production of hydrogen is usually we use methane. We react it with, I think it's water. No, not water. No, I'm sorry, I've forgotten what we react it with, but we react methane to get hydrogen from it. So, no, it's not. Well, it is renewable if we use biogas, but for the time being, we do use mostly natural gas to get hydrogen gas. So it's not completely carbon neutral and stuff. But, yeah, there are some unique problems that come up with using hydrogen. One such is that it has, while it does have a higher gram or kilojoule per gram, does it? Yes. It does, sorry. Yeah, it does have a higher kilojoule per gram. It has a lower kilojoule per liter because hydrogen gas is so undense, or it's not dense. Now, this comes to be very annoying as, we measure a car's tank in liters. So we have to have a lot of liters for a big tank, and we just can't fit that much hydrogen into it. There are, of course, upcoming technologies of hydrogen gas being absorbed onto a porous surface. For the most part right now, we have hydrogen as a liquid, which is a bit more dense, but it's still completely outclassed by most fossil fuels. There's also the issue of safety. As with most fuels, hydrogen gas is flammable. It's comparatively volatile as well. And we have to worry about the fact that hydrogen gas it's difficult to sense. So, if there's a gas leak, we can't smell it that well, unless of course we add dyes to it. But machines can't sense it as well, which is a big problem as, in a gas plant there are machines going off all the time, and there are sensors that sense even a small leak, and the small leak can obviously lead to something a lot bigger. Okay, but that's enough about hydrogen. You do need to know about hydrogen, though, specifically hydrogen. I want to talk about the function of this fuel cell. Now, this is a nice and easy fuel cell. It's what I'd say is a neutral fuel cell, because it's not acidic or basic. Both of these go in. Hydrogen ions go in here. Oxonium ions go in here. Oxonium? I don't think we call it oxonium, sorry. Oxygen ions go in here. They react to make water. Nice and simple. Happy days. And the water buggers off. We can also get two other different kinds. An acidic one, wherein this... I also should talk about this. The electrode. I'll talk about it after I talk about the other two. Where this is permeable only to hydrogen ions. So the hydrogen ions pass through. The oxygen, this cannot pass through. So as a result, these become common in the electrolyte. So it becomes acidic because hydrogen ions make things acidic. You will probably be asked to write the equations of a fuel cell. It's a lot easier if they're acidic, because you don't have to transform it to hydroxide. So it's just H2 goes into H, and all that easy stuff, simple stuff. Then there's basic. I've actually put a little bit of a mistake here as well. Hang on a sec. No. I'd like to see if people can spot it. I have literally just put my mouse under it, so if you can't spot it, it's a bit sad. No, but in this one, the electrode is permeable only to hydroxide. So the hydroxide passes through, it reacts with the hydrogen in this reaction to produce water, which is taken out here. Whereas this, the oxygen gas, is just reduced here, goes up through there. No, the electrons go up through there. No, the electrons go up into there, and the hydroxide goes through there. And as you remember, hydroxide ions make a solution basic. So this is what I would say is a basic basic fuel cell, sorry. Now, it's a bit of a tough thing, because there's a lot of different clever, sneaky ways to write if a fuel cell is acidic or basic or neutral. I mean, it's usually never neutral, but whatever. You can write it like this, be very kind to students, and just write hydroxide passes through. And, hydroxide's there, okay, it must be basic. But they can also mention something as simple as potassium hydroxide electrolyte. And then you have to think about potassium hydroxide, basic, or phosphoric acid electrolyte. Phosphoric acid acidic, that sort of thing. Or it might just give you a reaction that's like this. And you can see here that there's hydroxides and not hydrogen. So it must be a basic cell or alkaline cell. Which also leads me on to saying the mistake here is this. You need to add 2 hydroxides to either side. So it becomes 2H2OL plus 4OH. And that also leads me on to say, don't doubt cohas. Stuff can look a bit weird. You can say, how does this reaction produce water? Like when water's a product here. I mean, how does it take water when water's a product here? It does. You have to follow cohas. No matter how backwards it feels, it's generally always right unless you've got your basic key elements wrong. Now, I'd like to talk a bit about this part in particular, this beautiful electrode. Now, this electrode has some nice properties that make it very useful in this particular kind of cell. For one, it's very porous. This grants it a high surface area to volume ratio, which means more gas can get on it and react. It's also a catalyst, which means it speeds up that reaction. Though, considering fuel cells are a new technology, it's all very expensive, hence why the school doesn't have one. So they're not quite yet feasible in a lot of things, but I'm sure by the time we're a bit more grown up, we'll see fuel cells around. And that's pretty much the end of everything I want to say. There was one last thing. It was that I made a mistake on purpose on this cell. Yes. Now the mistake here is the solution does not cover the salt bridges and the electrodes. Something as simple as that. Whoops. Despite the fact that Miss, she obviously knows we understand that they have to be in the solution, she won't give you marks for it. I mean, it's as wrong as saying that there's a gigantic cut through here. It just doesn't make sense. And that it's the sort of thing that people just muck up. And they know it completely. They know it. Of course, they know the things have to be put in the water. But it's just they draw it wrong, they lose the mark. It's as simple as that. Now, I could have sworn there was something else. No, I think I covered everything. No. Yeah. Alrighty then. Okay, everyone. Thanks for watching. See you at the SEC tomorrow. Unless you're watching this in the future. I don't know why you do that, but... Anyway. Good luck on it, everyone. If you'd like to ask me a question, just go ahead. In the comments or at school. I want to have fun on Illustrator now. Alright, bye bye.